Albert Einstein's theory of general relativity has passed the most rigorous test till date. Numerous scientists, theories, and equations have made their mark in science and physics history. Scientists like Pythagoras, Aristotle, Galileo, Newton, Planck, and Hawking are famous examples. There are other ideas including Schrödinger's cat, Newton's apple, universal gravitation, and Archimedes' eureka, quantum mechanics. But Albert Einstein, his theory of relativity, and the popular equation E equals mc squared are probably the most well-known and renowned. In fact, relativity may be the most well-known scientific idea that only a small number of people really comprehend. However, there have always been others who have sought to refute Einstein's general theory of relativity. However, it has so far passed every test. The most rigorous test to date, according to recent studies, appears to have been passed by Albert Einstein's theory of general relativity, which strengthens its position. So let's examine what this test entails, and what did it prove. Despite being around for more than a century, researchers have shown that Einstein's theory of general relativity is accurate to a remarkable degree. The weak equivalence principle, which asserts that all objects regardless of their mass or composition should free fall in a specific gravitational field in the same manner, when interference from factors like air pressure is eliminated, was the focus of the study team's efforts. In order to do this, the researchers used the French satellite MICROSCOPE, which was launched in 2016 to measure the acceleration of objects in free fall. Let me explain it simply. If you simultaneously drop a feather and a stone towards the Earth from the same height in an atmosphere with perfect zero resistance, which do you think would contact the ground first? The principle of equivalence states that both things should fall to the Earth simultaneously, despite the common misconception that because a stone is heavier than a delicate feather, it should suffer greater gravitational pull and reach the ground first. In other words, the acceleration of a body is independent of its physical makeup, because its inertial and gravitational masses are proportional to one another. What distinguishes gravitational mass from inertial mass, then? Inertial mass is the same name given to the mass that appears in Newton's second law of motion. It merely states how challenging accelerating a thing is. On the other hand, the mass that occurs in Newton's universal law of gravitation is the gravitational mass. It represents the force with which gravity operates on a body. Therefore, even though a stone has more gravitational mass than a feather, the force of gravity acting on it is larger and its inertial mass is also greater, making it difficult to accelerate. As a result, the two effects cancel each other out, causing it to fall with the same acceleration as a feather, exactly the same acceleration caused by gravity during free fall. If there is even a slight deviation from the proportionality between inertial and gravitational mass, Einstein's entire theory collapses. This highlights how crucial it is to conduct experimental searches for these breaches. When astronaut David Scott simultaneously dropped a feather and a geological hammer during an Apollo 15 moonwalk, both objects accelerated towards the moon surface at the same pace due to the lack of air resistance, making it one of the most famous tests of the weak equivalence principle. Similar free-falling test masses constructed of platinum and titanium alloys are carried by microscope. Any variations in the applied electrostatic force must be the consequence of variations in the test mass's velocities, since electrostatic forces maintain their relative locations to one another. The team's findings, which represent the culmination of 20 years of research, showed that the difference in acceleration between two objects in free fall was no larger than 1 part in 10 to the power of 15, and that no violations of the weak equivalence principle larger than that were discovered. The results constrain any deviations from the weak equivalence principle, and also rule out any general relativity deviations from Einstein's 1915 theory of gravity. The microscope mission began in April 2016, and mission personnel published their initial findings in 2017. Even after the experiment's conclusion in 2018, data analysis has continued ever since. The strongest limits on this aspect of general relativity have been placed on it by the recent researchers' failure to detect any violations of the weak equivalence principle, and the findings also provide the foundation for future studies that will be even more sensitive. That's as a result of the researchers' inclusion of recommendations for enhancing the experimental design they employed. They suggested possible improvements, such as smoothing out satellite coding flaws that could affect acceleration readings and switching to wireless systems in place of wired ones. With these upgrades, a satellite may be 100 times more sensitive than microscope and detect weak equivalence principle violations as little as 1 part in 10 to the power of 17. The microscope experiment will continue to be the best way to test the weak equivalence principle for the foreseeable being, according to the team's prediction that these enhancements won't be possible for a while. For at least 1 decade or maybe 2, We won't see any improvement with a space satellite experiment. Manuel Rodriguez, a MICROSCOPE team member and a scientist at ARNERA, a French research institute specializing in aerospace, said in the statement. However, general relativity fails at the atomic and subatomic scales and is replaced by quantum mechanics. Differences between the two have long been a source of debate among scientists. One approach might be to identify the precise point at which general relativity fails. Since Einstein's two papers from 1905, one describing the quantum and the other defining relativity, the battle between the two branches of physics has been simmering for more than a century. However, in recent years, the dispute has entered an intriguing and unpredictable new stage. In their respective camps, two eminent physicists have taken extreme stances and are now undertaking tests that may ultimately determine which strategy is best. The distinction between the quantum and relativity systems might be summarized as smooth versus chunky. Events in general relativity are continuous and deterministic, which means that each cause corresponds to a particular local result. The outcomes of events caused by the interaction of subatomic particles in quantum physics are probabilistic rather than certain, and they occur in jumps. Yup, quantum leaps. Connections permitted by quantum laws are not permitted by classical physics. In a recently published experiment, Dutch researchers disproved the local effect, demonstrating this. They demonstrated how two particles, in this case electrons, may quickly affect one another while being a mile away. Things do get horribly wrong when you attempt to understand chunky quantum laws or smooth relativistic laws in other direction. When you try to scale relativity down to quantum level, it provides illogical results and eventually describes gravity with infinite values. Similar problems arise when quantum mechanics is scaled up to cosmic dimensions. Even in what appears to be empty space, quantum fields carry a certain amount of energy, and the quantity of energy increases as the fields get larger. The message of E equals mc squared is that energy and mass are identical, hence accumulating energy is precisely like accumulating mass. If the quantum fields are large enough, they can produce a black hole that will eventually force the cosmos to collapse in on itself. If gravity isn't a force, how does it accelerate objects? Which is possibly the most crucial and frequently asked query about general relativity. According to general relativity, energy determines how space-time bends and how that energy moves. Energy can take on several forms including mass, light, and other types of energy. The idea of gravity is that objects are falling as a result of space-time bending. A geodesic is the name for the path that objects take. Let's start by examining the bending aspect of things, and then we'll return to examine geodesics. An object's energy and the amount of bending it causes are inversely proportional. Typically, the most important part of its energy is its mass energy, but there can be exceptions. In our solar system, the Sun's mass has the greatest impact on bending. It dwarfs the Earth's contribution to the bending of space-time to a point where, roughly speaking, we may merely assume that the Earth is massless as it orbits the Sun. We call this the test particle limit. Similar to this, when you're standing on Earth, the Earth's mass dominates the bending of space-time over your own. Thus, you can consider yourself to be a massless test particle for all intents and purposes. However, the truth is that when you twist the space-time around you even little, the Earth is affected as a result. Let's return to those geodesics now. A body in geodesic motion is impervious to external forces. Only what appears to be a downward slope across space-time is being followed. This is how the bending affects the motion of an object. Surprisingly, an object's desired geodesic is determined by its velocity rather than by its mass, unless it is massless, in which case its velocity is exactly the speed of light. We refer to this body as being in freefall because it is not being affected by any forces. No force is being applied by gravity. In conclusion, general relativity states that matter causes space-time to bend, and that this bending results in the creation of a generalized sort of force that acts on objects. However, the object isn't being affected by a force per se, rather it is only traveling along its geodesic arc across space-time. The general relativity theory has long served as the gold standard for all of physics, but its breakdown at the atomic and subatomic levels show that it is not universal. However, it must withstand exhaustive testing. But what if it doesn't work? Then the entire field of physics will need to be reviewed. As a result, science places a high value on it.